So here we have the graph of a function. F of x is equal to x squared minus x minus 2. And the graph is drawn pretty much to scale. So what I'm going to do is focus on the behavior of this function at a particular point at x equals 1. Now, here I've marked a point on the graph of f of x at x equal to 1. And I've labeled the point here with the x-coordinate 1 and the unknown y-coordinate. To get the y-coordinate, we have to substitute x equals 1 into the function. So, to compute f of 1, we substitute x equals 1, we get 1 squared minus 1 minus 2, and that gives us minus 2. So, this point on the graph of f of x is x equals 1, and y is minus 2. Now, this line here indicates the slope of the graph of f of x at x equals 1, because it is tangent to the graph at that point. So, notice that the line just touches the graph only at this one point. It does not cross the graph. So, the slope of this tangent line, and if indicated here, we do not yet know the equation of this line. The slope of this tangent line is the instantaneous rate of change of f of x at x equals 1, also known as the derivative of f of x at x equals 1. So the slope of a tangent line at x equals 1, which is equal to the instantaneous rate of change at x equals 1 is given by f prime of 1. So this is notation we use to indicate this instantaneous rate of change, which is also the derivative of f of x at x equals 1. Now, to obtain the derivative, we take the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And that comes from, if we were to choose any point, so here we have x equals 1, so here we have x is equal to 1 plus h. So what I could do is compute the equation of a line between these 2 points and find the slope of that line. And this is called a secant line that corresponds to these 2 points. But now, as we can see, the slope of that line is not the same as the slope of a tangent line. But if I were to move this point closer, if I were to choose h smaller, then whatever secant line I would draw would more closely approximate this tangent line. And as h gets smaller and smaller, the better that approximation gets. So finally, I could see what happens as h approaches 0 and find the slope of a tangent line. Now, suppose I were to substitute h equals 0 in this expression. I would get f of 1 minus f of 1, which is 0, divided by h, which is also 0. So I have 0 over 0, which is undefined. It's called an indeterminate form. So I can't simply substitute h equals 0. And that's why we need to take a limit. We need to see what value this expression is approaching for non-zero h that is getting smaller and smaller. So what I will do now is substitute my function f of x in here. So here we're substituting x equal to 1 plus h. So use parentheses. So I'll have 1 plus h squared. You'll see why I'm using 2 parentheses in a moment. Minus x, which is 1 plus h, minus 2, and I put that in parentheses. So this is f of 1 plus h minus f of 1. But we already have f of 1. That was computed earlier. That's equal to minus 2. So I'll put that in there. And then we divide by h. And I was supposed to put this expression, the limit as h approaches 0. Okay, so continuing, we need to simplify this, see what happens as h goes to 0. So I'll remember to put my limit in here again. So we have to multiply this out, 1 plus h squared. So that would be 1 plus 2h plus h squared minus the quantity 1 plus h, so minus 1 minus h, minus 2, and then minus a minus 2, all over h, still divided by h. And now, several things cancel out, several terms cancel out. So we have these 1's cancel out, and then the minus 2, minus the minus 2, those cancel out. And here we have like terms combining, the 2h and the minus h will give us an h. So now we have h plus h squared all over h. But now what I can do is I can factor an h out of the numerator. So now I have h times 1 plus h all over h. But now the h's above and below cancel out. So now what I have is the limit as h goes to 0 of 1 plus h. Now we can simply substitute h equals 0 because there's no danger of dividing by 0 or getting 0 over 0. And we obtain 1. So we conclude that f prime of 1, the instantaneous rate of change of a function at x equals 1, is equal to 1. And that is the slope of our tangent line. And if we look at the graph, I don't have the scales written down here, but actually this is a line that has a slope of 1. So now that I have my value of f of x at x equals 1 and f prime of x at x equals 1, I can obtain the equation of the tangent line at x equals 1. So to obtain the equation of a tangent line, I have y equals the value of my function at my point. So this is at x equal 1. So I have the value of a function at my x value, 1, plus the value of the derivative, the slope of a tangent line at x equals 1, times x minus 1. So this comes from the point slope form for the equation of a line. So now I can fill in all my information. So f of 1 is equal to minus 2, and then f prime of 1 is equal to 1 times x minus 1. So then now I can simplify all of this. So I have y is equal to x minus 2 minus 1, so x minus 3. So this is the equation of my tangent line that is drawn here. And sure enough, the function is equal to minus 2 at these 2 points, and here the tangent line is crossing the y-axis at y is equal to 3, so minus 3. So this is the y-intercept of minus 3 that shows in our equation, and the slope of 1. So value of a function at a given point, with the y coordinate, if I put it in the graph, is obtained by plugging your x value into the function. To get the slope of a tangent line, or instantaneous rate of change of a function at that x value, you have to compute the derivative at that point. And currently I'm using the definition of a derivative to get that value. But in upcoming sections, we'll learn differentiation rules to achieve that a whole lot more easily.